Okay, we're going to talk about L'Hopital's rule now. L'Hopital's rule. L'Hopital's rule is a tool that we can use to evaluate limits which might be otherwise difficult or even impossible to evaluate without it. I guess I should say right from the start that L'Hopital's rule was not invented by L'Hopital. The man is an imposter and a thief. Now, maybe that's a little bit harsh. It's actually invented by Bernoulli, but L'Hopital was paying Bernoulli to come up with things, so L'Hopital was the money man, and he got his name in his textbook. Anyway, L'Hopital's rule. I don't know what's the matter with these markers today. What does L'Hopital's rule say? Let's suppose that we want to evaluate a limit as x approaches some value of one function divided by another. Now, when evaluating limits, the first thing that we always try is direct substitution, plugging in c here. Well, sometimes what will happen is when you plug in this value, you will get an indeterminate form. All right? If in this limit, direct substitution have I crossed my T's and dotted my I's? If in evaluating that limit, direct substitution yields an indeterminate form, zero over zero, or plus or minus infinity over plus or minus infinity, then this limit equals the limit of the quotient of the derivatives. Oops. All right? If in that case, now it does not work if direct substitution does not yield an indeterminate form. But if it does, then we can take the derivative of the numerator divided by the derivative of the denominator, evaluate that limit. And it will be the same as this limit. And we can use this as many times as is necessary as long as we get an indeterminate form. So if you try to evaluate this now by direct substitution and get the indeterminate form again, you can take the next derivative of the numerator and the denominator. But notice two things I am not saying. I am not saying that the quotient here equals the quotient there. No, just that limit, the limit of that quotient at this particular x value. I am also not saying use the quotient rule. Students often will make this more complicated than it needs to be. This is much simpler than the quotient rule. It is just the derivative of the numerator over the derivative of the denominator. So do not use the quotient rule. Okay? So, those points. Do not use it if you don't get an indeterminate form. If you use it without an indeterminate form, L'Hopital's rule will often give you a very reasonable looking wrong answer. All right? Don't do it. Okay, so that's what L'Hopital's rule tells us. Now, something that we should be aware of is this. L'Hopital's rule will always work when we get these, but it's not the only way to solve all indeterminate forms. In fact, in our really elementary study of limits, we had other methods for some limits yielding indeterminate forms. And let's go back. This was before we ever did a derivative. One of the first limits that we ever saw was this limit. The limit as x approaches 1 of x squared minus 1 over x minus 1. We did not have L'Hopital's rule at the time. We didn't have derivatives. And we saw that if we plugged in 1, we got 0 over 0. At that time, we said, well, we can evaluate that limit by factoring and canceling. That is, for all x approaching 1, not equal to, but approaching, no matter how close, this function is equivalent to x plus 1. And the limit could be found by simply plugging in 1 for x, and the limit was 2. That is, as x approaches 1, y approaches 2. And we even showed the graph of that function to be exactly identical to the line y equals x plus 1, with the exception that at the point 1, 2, we had a hole. As x approaches 1, y approaches 2. The limit exists, even though the function is not defined at x equals 1. That was one method we used, factoring and canceling. Another method for other function types, well, we had functions like this. The limit as x approaches 4 of 1 over x minus 1/4 over 4 minus x. And we saw that if we plugged in the 4, we had 1/4 minus 1/4, which is 0 over 4 minus 4, which is 0, indeterminate form. But at that time, we said, well, we have an algebraic manipulation that will do the job here. We'll multiply both numerator and denominator by the common denominator of these two fractions, that is 4x. And in so doing, this becomes the limit as x approaches 4. 4x times 1 over x is 4. 1/4 times 4x is x over 4 minus x times 4x. This divided by this is 1. Now we can plug in the 4 without getting an indeterminate form, and we have 1/16. In either of those two cases, L'Hopital's rule would work. Let's just go back to the first one. The limit as x approaches 1 of x squared minus 1 over x minus 1. All right, we get the 0 over 0. So we could say, by L'Hopital's rule, I like to make that little notation just to signify that I am using L'Hopital's rule to go from this line to this line, equals the limit as x approaches 1 of f prime over g prime. And now as x approaches 1, we have 2 over 1, which is 2. The same thing we got previously. And we could do the same with that one. Okay? L'Hopital's rule will always work when we get an indeterminate form, but it's not always the only method. All right, so let's take a look at one limit where we don't have the other options. We cannot factor and cancel. We cannot multiply by a common denominator, or the third method we used when we had radicals was to multiply by conjugates. Let's take a function that does not open itself to any of those methods. Suppose we wanted to find the limit as x approached 0 of sine squared x minus e to the x plus cosine x divided by ln x plus 1 plus the tangent of x. Okay, if we plug in 0 here, we get 0 minus 1 plus 1. That is 0 over the log of 1, which is 0, plus the tangent of 0, which is 0. There's nothing to factor and cancel. There's nothing else that we can do. There's nothing we can do algebraically here. But L'Hopital's rule solves the problem for us. Because this yields the limit as x approaches 0 of derivative up there. We'll practice for our chain rule. 2 sine x cosine x. I hope you recognize that that's the sine of 2x, trigonometric identities, minus e to the x minus sine x divided by 1 over x plus 1 plus secant squared x. Now when we plug in 0 here, well, the sine of 0 is 0, so we got 0 minus 1 minus 0. Plug in 0 here, we get 1. The secant of 0, like the cosine of 0, is 1. 1 plus 1 is 2. And our limit is negative 1/2. Okay, we'll continue in our next video.